Okay, there are actually two things that we're going to be talking about in the next topic, which is relays. And these two things directly affect the current lesson, which is motors, digital motors. And how do digital motors have anything to do with relays? I mean, if you knew what a relay doesn't move at all. Well, sort of. First of all, let's talk about that old childhood toy that we used to, well, toy is the wrong word, childhood game that we used to do, where we would take a wire and wrap it around a nail, some sort of a large nail, and then connect that large nail or connect that wire to some, like a dry cell, some sort of a large, battery. And by sending current through that wire, what we were doing was we were generating an electromagnetic field. If you look at a basic wire, just a wire by itself, if we send current through that wire and we put the thumb of our right hand in the direction of the current, we see that we are creating an electromagnetic field around that wire. When we wrap that wire around, what happens is all of those electromagnetic fields are focused. They kind of, well, they're wrapping around that wire, and you've got this focus of all of the electromagnetic field going through the nail, coming out and coming back out the other side. So if I have current flowing through this wire in this direction, put my thumb of my right hand in the direction, you see that there's a little coil, a little electromagnetic field that is wrapping around each one of those wires. And when they sum up together, what you've got is this, on the outside, the coil, the electromagnetic field is coming out and then coming back in one end of the nail and coming out and going back in the other end of the nail. And what happens is all the sum of all these little electromagnetic fields running through the nail magnetizes the nail. Okay, so what we're going to do is we're going to take another, piece of metal, and we're going to wrap this wire around it. And we're going to take our fingers of our right hand, and if I have my current flowing in that direction, I'm going to take the fingers of my right hand, put them in the direction of the current going through the coil. This works also for the coil, and we're going to see that my thumb is pointing in the direction that the electromagnetic field is being created. So it's going to come down, out through the bottom of the coil, and come back up on the outside. Now, by magnetizing this coil, what we've done is made it so, well, we can attract a piece of metal, right? And so what I can do is I can take some sort of a piece of metal on a pivot here and actually have a spring, something that'll put force down on one end of it so that whenever there's no current flowing through that coil, then, and this little block of metal on the inside is not magnetized, then the pivot, I'm going to pivot away from the coil, and I'm going to disconnect the, I'm just going to disconnect the metal from the magnet. But as soon as I magnetize this, then what's going to happen is this guy is going to swing down so that it becomes connected with that piece of metal. Now, it's not this connection that we're interested in. The connection that we're interested in is if I were to take and put some sort of probably be a better way to erase this. If I were to make it so that I have a lever on one end, and so whenever it's open, the lever is away, and whenever I close it or whenever I put the electricity through the coil and it attracts that lever will actually push some sort of a connection to another another wire, to a flexible piece of wire. And whenever I make this whenever I run current through this coil and it pivots that lever, it's going to push this wire so that it is in connection with the second wire. And what you have is the ability to have current flow from one terminal into another one. Now, That seemed like a not very graceful way to explain how this all works. But in general, what we're doing here is as soon as I electrify this, and this lever pivots, and it pivots to the point where it takes two pieces of metal and makes them contact each other, what I can do is I can make it so that this piece of wire can handle a significant amount of current, whereas this piece of wire just needs to be able to handle enough current to magnetize the coil. So, whenever we've got this idea of a relay, there are a couple of very important things that we're doing. First of all, notice that there is no physical connection at all between the wires on this end, which is referred to as the primary, and there's no physical connection of the wires on this end with the connection or the terminals on this end, which is referred to as the secondary. All right. Now, that means, first of all, we've got something called electrical isolation. All right. That's the first thing that a relay gives us. The second thing that a relay gives us is that the current that is necessary in order to activate the primary, in order to make it so this lever moves, that amount of current can be significantly less than what the secondary is capable of carrying. So what we've got is this ability to control large amounts of current with low current. All right, and I've kind of filled up my board here, haven't I? I'll peek to you through some of the drawings. So this idea of being able to take a little bit of current, run it through a coil in order to turn on and off large amounts of current is really important whenever it comes to microprocessor design. One of the reasons why it's really important for microprocessor design is because the outputs coming from a microprocessor, they're not capable of having a lot of current. But we may want to control things like fans, motors, lights, things that have large current draw that the processor is not capable of delivering. We can at least control it with a relay, okay? Now, there's a second type of relay called a solid-state relay. Let me make some room on this board before we talk about the solid-state relay. Before we move on to the solid-state relays, let's take a look real quick at how the schematic looks whenever you're trying to represent a relay. Now, typically what you've got is some sort of a coil representation on the schematic, which identifies the primary. All right. Now, you may even have some lines that identify the fact that we've got this core that's being magnetized by this coil. Now, what ends up happening is you typically have something like a dotted line or something showing control to possibly, and there's a number of ways this could happen, but to some sort of a switch, okay, that can be pulled down one way or the other way. Now, what typically happens is this switch is going to be identified as touching, let's get this cleaned up a little bit better, as touching one of them whenever it's not powered. In other words, when we don't have any current flowing through this coil, that switch is going to be all the way raised up into this connection right here. Now, what this is going to be referred to as, it will be called the normally closed connection, or NC, which means that if it's powered off, in other words, we don't have electricity flowing through this primary, then you're actually going to have a closed circuit here. And at that same time, between these two connections, you're going to have a normally open, or NO situation. So the way it works is that when you get this particular relay, it's going to show that I'm going to have some contacts that are normally closed, some contacts that are normally open. That means that when the primary has no power at all, then the secondary these two connections are going to be closed. The top two, the normally closed connections, are going to be closed, and the normally open are going to be open. Well, let's go ahead and put power or put current through our primary. It's going to magnetize this and pull the switch down. And whenever it pulls the switch down, then the normally open is going to be closed. We're not changing the name of the contacts. These are still the normally open contacts. What this means is whenever we don't have power or current flowing through the primary, this set of contacts is normally open. When we do have a current flowing through the primary, this set of contacts becomes closed. Vice versa, when we don't have current flowing through the primary, the normally closed is contacted. There's a switch closed. But whenever we do have current running through the primary, the normally closed opens and no current is flowing. All right? Let's move on to solid state. All right, now the solid state relay works a little bit differently, but it works on the principle of something called opto-isolation. Now, opto-isolation takes care of one of those principles that I was talking about with the relays. Remember, there were two principles or two benefits. One was isolation, and the other one was the ability to control large amounts of current with small amounts of current. Let's talk a little bit about opto-isolation. Opto-isolation is, instead of isolating things electronically using electromagnetic waves, now we're going to isolate it using optics. Light, okay? So picture that we have an LED. So I've got an LED here, all right? And it gives off light. And on the other end, I've got what we're going to refer to as a phototransistor. Now, I'm not really concerned if you understand the idea of a transistor and the PNP doping or the NPN doping of a transistor and how, the depletion region and so forth works. What I really just need you to know is that a transistor is really a switch. And whatever is coming in from this portion of the switch, the base, that portion of the switch, whatever is coming in there, controls whether current is flowing through this transistor or not. Well, in the case of a phototransistor, instead of electricity turning on and off this switch, light turns on and off the switch. If there's no light, the switch is off, no current is flowing. If the light is on, then the switch is activated and current can flow. Now, you put all of this inside of a package, you can't actually see it because the light is all contained inside of an enclosed package, but what you've got is, once again, isolation. You've completely separated the input side from the output side. Now, remember, there were two things. The first thing was isolation, but the second thing was the ability to control high current with low current. Your microprocessor has more than enough current in order to control an LED, to turn on and off an LED. The phototransistor, the rating of the phototransistor, if it's rated high enough, you can carry much larger amounts of current than you could if you were just trying to control it with the processor. So this, a solid state relay, instead of using the idea of coils in order to separate, because the electromechanical relay uses electromagnetic waves or magnetism in order to isolate, to go from the controlled primary to the secondary, whereas the solid state relay is using light to go from the primary to the secondary. Now, what does this have to do with our motors? Well, first of all, whenever we're talking about digital motors especially, so we're talking about things like stepper motors, brushless DC motors, and so forth, those motors are controlled electromechanically, much like the coil is magnetizing that piece of metal inside in order to attract the switch. Well, with a motor, what we're doing is we're magnetizing coils. We're using coils to magnetize pieces of metal in order to turn a magnet and give you motion, rotational motion. But We're also going to be looking at this idea of opto-isolation, because what we can do is, in order to determine how fast something is spinning or what direction it's spinning, we can use this same idea of an LED transmitting to a phototransistor and being able to determine if we can see light or we don't see light. If we pass like a rotating disc or something with slots in it, you can actually count how quickly the light turns on and the light turns off based on whether or not the phototransistor is receiving an output from the LED. There you go. So the idea of relays, something that doesn't move at all, actually plays a big part whenever it comes to rotational movement for our DC motors and the way we detect what the position of that motor is.